This is the 7.2 notes on VSEPR. In the last lecture, we talked about Lewis structures and how we can show how the atoms in a covalent molecule are bonded. The shape, though, of a molecule is going to be determined by the arrangement of lone pairs of electrons and the bonding atoms that are around it. So, for instance, the following are all correct Lewis structures for water, these on the left right here. So these are all two-dimensional representations of water, what we call Lewis structures. And technically they are all correct, they just look a little bit different. Sometimes the shared electrons are actually shown as dots, and sometimes they're shown as dashed lines, but technically they're all correct. So the number of valence electrons is correct, and the octet rule is being followed. However, if we tried to use these as the basis for what water looks like three-dimensionally, we would get different shapes. So the first one might look like atoms in a line, and this one looks like they're bent, and this one looks like it's at 90 degrees. So these 3D shapes are all different. To bridge the gap between the two-dimensional Lewis structures and what water actually looks like three-dimensionally, we have to use something called the valence shell electron pair repulsion theory, or VSEPR for short. VSEPR is based on the fact that electrons are negatively charged, and because they're all negatively charged, they repel each other due to these electrostatic forces. VSEPR predicts the shape of the molecules by maximizing the distance between these negative electrons. This gives rise to the following basic shapes that we're going to see. So we have linear, which looks like this. The next one is trigonal planar. We have bent, tetrahedral, and finally trigonal pyramidal. So around the central atom, we can have either lone pairs of electrons, the two dots that we show, or a shared pair of electrons between two atoms. That's when we draw the line. These are what we call areas of electrons, or electron domains. So the number of lone or non-bonding pairs of electrons present will actually change the shape of the molecule. So for water, we have lone pairs of electrons up here, these dots, and then we have shared pairs. And so in total, water, this oxygen in water has electrons here, 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 and here. So it actually has four areas of electrons, or what we call four electron domains. If I have three areas of electrons, and all three of them are bonding pairs, that means that there's three bonded atoms around it, and this shape is going to be trigonal planar. Trigonal planar. But if one of these is a lone pair of electrons, that means that I have electrons occupying the space here, but no atom that's bonded to them, then I'm going to get this bent shape instead. So the shapes that we have are going to depend upon the number of bonding atoms and the lone pairs of electrons. So we start out with our electron domains, how many areas of electrons we have around us. And if there's only two, then we're going to have a linear shape. So here we have this central atom and two areas of electrons around it, and we get a linear shape. If I have three pairs of electrons, then the three pairs can either be connected to bonding atoms, or I could have two bonding atoms and one lone pair of electrons. So remember that lone pair is all by itself. So if I have three bonding atoms, my shape is going to be trigonal planar. But if I only have two bonding atoms and I have this lone pair of electrons, then I'm going to have a bent shape. Oops, bent shape. So lone pair of electrons, bent shape. If I have 4 pairs or electron domains, 4 electron domains, either all 4 of them can have bonding atoms, 3 can be bonding atoms, and 1 can be a lone pair, or I can have 2 bonding and 2 lone pairs. So what I can get is if I have all 4 atoms attached to that central atom, I'm going to have something called tetrahedral. If I have 3 atoms attached and I have a lone pair of electrons occupying some space, that's going to be trigonal pyramidal. And then finally, if I have 2 atoms attached and 2 lone pairs of electrons, that's going to be a bent shape again. Slightly different bent shaped, but it's called bent. So, to summarize, if I have 2 electron domains, my electrons are here and my atoms are out here, and I get a linear shape. If I have 3 electron domains, here again are my atoms, and so I'll be trigonal planar. I can also have a bent shape if I have 2 atoms and a lone pair. That's just not pictured here. And then finally, if I have 4 electron domains, I can have 2 of them have atoms. And here I have my lone electrons in occupying space up here. And so because they're occupying space, they're actually pushing these others. Remember, we have electrons right here. They're just being shared. And so all of them want to get as far away from each other as possible. So that's why these are being pushed down. And so I get bent. If I have all 4 connections or electron domains occupied with atoms with shared pairs of electrons, then I'm going to get this tetrahedral shape. And so we get tetrahedral because it makes triangular prism almost out of that shape. And then finally we have if one of them is a lone pair and then I have 3 atoms, I'll get the trigonal pyramidal. And the trigonal planar and the trigonal pyramidal kind of look similar. So especially if you look at it from the top, they look the same. And so it's making this triangle. But if you look at it from the side, and that's where you're going to see the difference. All 4 of these atoms here in the trigonal planar are all on the same plane. So they're occupying the same plane. Whereas this one, it's not in the same plane. It's actually forming a little pyramid. If I put it back down, there's space right under here because the blue one is not touching the surface. Whereas with this one, all the atoms are touching the same surface. They're on the same plane. Okay, so we can take our Lewis structures and use those to predict what our 3-dimensional shape is going to be, what our VSEPR shape is going to be. So the shape for CO2 and SO2. So the first thing we have to do is create Lewis structures. So for CO2, the first thing we need to do is the math. I have 4 valence electrons from carbon, and I have 2 times 6 valence electrons from the oxygen for a total of 16 electrons. Or 8 pairs. Next, I choose which atom is going to go in the center, and that's going to be my carbon. So carbon will go in the center. I'm going to attach the oxygens around it. And so I've used 2 of my 8 pairs. There's my 3rd, 4th, 5th, 6th, 7th, and 8th pair. So all 8 pairs are now used. However, my oxygens all have 8 around them, but my carbon does not. So if you recall from learning how to do Lewis structures, we're going to make these oxygens share their electrons so carbon gets them also. So carbon ends up with double bonds to the oxygens, and the oxygens have some lone pairs. So to figure out the shape, what we're going to do is we're going to take the central atom, just the carbon. We're basing this on the central atom. And around carbon, I have electrons in this area I know it's a double bond, but all 4 electrons are occupying the same space. And I have electrons in this area. So I have 2 electron domains, or 2 areas where the electrons are. So the overall shape, there I have my center atom, I have 1 bonded atom and a second bonded atom. The shape is going to be linear. For SO2, it's going to be slightly different. S actually has 6 valence electrons, and then from the oxygens, an additional 12, so that's going to give me a total of 18 electrons, or 9 pairs. So similarly, I'll put sulfur in the center, oxygens go on the outside, adding my other electron pairs. First to oxygen, I've used 8 of my 9. My 9th pair goes right there. Everybody is almost happy. All of my oxygens are happy with 8 around them. But my sulfur is not. My sulfur only has 2, 4, 6 electrons. It needs 1 more pair. And it doesn't matter because both of these are oxygens. It doesn't matter which one I make share. I'm going to make this one share his pair of electrons. I could have made the other one. That's fine. But just sharing 1 pair makes everybody happy. If I tried to share 2, then all of a sudden sulfur would have 10. And it doesn't need 10. It's happy with 8. So my shape is going to look like this. There's going to be a double bond on one side and a single bond on the other. And it still has that lone pair of electrons. So this oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And the sulfur has 2, 4, 6, 8 electrons around it. Everybody's happy. I've used 9 pairs total. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the Lewis structure. And again, so if I take the center atom and I count how many areas of electrons I have around it, I have electrons here in this area, I have electrons here in this area, and finally I have electrons here in this area. So that's a total of 3 electron domains. 2 of these have atoms on them, and the third one is just a lone pair. So that's going to give SO2 a bent shape, because that lone pair of electrons is occupying space also. It's going to be pushing these shared pairs of electrons down. So you have to do a Lewis structure first before you can figure out the VSEPR, or the molecular geometry. Now, just as bonds between 2 atoms can be polar if the electrons are shared unequally, if the atoms unequally share electrons, this creates partial negative and positive charges, and similarly, an entire molecule can actually be polar or nonpolar. So to figure out if the entire molecule is polar or nonpolar, we have to look at the shape and the distribution of the electrons for each bond. So we have to look at each bond first and then take it up as a sum up all of them. When the polarities of the bonds are looked at collectively, the molecule as a whole may or may not be polar. So let's take a look at some examples. Let's say all our bonds are nonpolar. So if all the bonds are nonpolar and the electrons are shared equally, then I have no partial negative or positive parts to the bonds, and therefore I have no partial negative or positive sides to the entire molecule. So that molecule will be nonpolar. An example is right here. Remember, carbon and hydrogen are nonpolar bonds. So these are nonpolar bonds. That means that there is no partial negative or partial positive to these. And so my entire molecule, and this is carbon, the black one is carbon, and then the white ones are hydrogens. All of these are shared equally. So the entire distribution of the electrons is equal. That means that this is going to be nonpolar. Now let's say I do have some polar bonds. So let's say I have polar bonds, but they cancel out. So when my bonds are polar, it's like a tug of war between atoms for the electrons. However, if all of the tug of wars cancel each other out, then the molecule as a whole does not have a positive or negative side to it. And again, the molecule will be nonpolar. So in our analogy, here we are playing tug of war, and both sides are pulling equally. And if they're pulling equally, that means it's going to be nonpolar. But if one side is pulling a lot more than the other side, then there's going to be a side that wins, and they're going to win all the electrons, meaning that that side is going to be negative. And the other side is going to be partially positive. And so this entire molecule then will have a partial negative side to it and a partial positive side of the molecule, not just the bond, the molecule. So here I have polar bonds. All of these are polar. The carbon chloride bonds. There's 4 of them, and they're all polar bonds. So it looks like here, this. I have carbon in the center and chlorine on the outside. This chlorine is pulling downwards, and this one's pulling this way, and this one's pulling this way. But they're all pulling equally. And so if I flip this around, no matter where I flip it, these are all equidistance away. And so they actually cancel each other out. So even though my electrons are crowded around the outside atoms, they're all pulling equally in different directions, and so it cancels out. And so this is again nonpolar. Even though my bonds are polar, the molecule is going to be nonpolar. And so if I show my dipole moments, my electrons are being pulled. These are polar bonds. They are being pulled outwards, but they cancel out. All right. And the last situation is if we have bonds that are present that are polar, but they do not cancel out. So if the bonds are polar, but are pulling in such a way that there is a winner in a tug of war, that means that there will be an area on the molecule with a partial negative charge, where all the electrons are kind of going towards, and a different area with a partial positive charge. And so this molecule will be polar. So I have 2 examples here. In this first one, I have 3 hydrogens and 1 chlorine. And in the second one, I have 3 chlorines and 1 hydrogen. And with this, my carbon-chlorine bond is polar, and therefore pulling the electrons towards the chlorine because it's more electronegative. But my carbon and hydrogen bonds are nonpolar. So there's really only pull in one direction, and the other ones are not pulling at all. So because the electrons are going towards the chlorine, that's going to be a partial negative part of the entire molecule. And then the other side is going to be partially positive. So even though these are going to be nonpolar bonds down here, the entire molecule as a whole has a negative side and a positive side. It's a polar molecule. Just like we have North Pole and South Pole, this has a negative pole and a positive pole. For the other one, my chlorines are actually pulling the electrons all towards themselves. And again, the carbon and hydrogen bond is going to be nonpolar. And they're going to share the electrons equally. But my carbon and chlorine bonds are polar. So in this instance, again, it's unequal pulling of the electrons, and the chlorines are all pulling downwards, but my hydrogen is not pulling equally upwards. And so I will again end up with a positive part of my molecule, of my entire molecule, and a negative part of it. So this molecule is polar. All right. So if no one wins because they're all pulling equally on the tug of war, that's going to be nonpolar. If one team is pulling more than the other teams are, then there's going to be a winner. And so this is going to be polar. Here's my winner. And then finally, if I only have two teams pulling, and so let's say right here, this is a non-polar bond because nobody's pulling, but these two guys are. Even though they cancel each other out left and right, they're all pulling downwards, whereas this guy is not pulling at all. And so again, overall, it's being pulled in one direction. There is a winner. Both of these are winners, so here. This one is not. And so this is going to be a polar molecule. So, is water polar or non-polar? And if so, if it is polar, what are the partial charges? So the Lewis structure for water looks like this. And remember, water has 4 areas of electrons around it, 4 electron domains. And so because 2 of them have bonds, bonded atoms, and 2 are lone pairs, the overall shape is going to be bent. And my lone pairs of electrons are up here. Now, this is a polar bond. Oxygen, hydrogen, that's a polar bond. The oxygen is pulling the electrons towards itself. So in a tug of war, the oxygen is pulling the electrons towards it, and the hydrogens are not pulling equally in the other direction. So there is a winner. So that means that water is going to be polar. The oxygen side of it is taking all the electrons. So that side is going to be partially negative, and my hydrogen side is going to be partially positive then.